All right, so what we're going to do today is we're going to look at some examples from chapter 16, and I'm going to work them out and kind of talk through them. So if you're having trouble with a particular type of problem, maybe if you see it demoed, it'll give you a little bit of clarity with that material. Okay, so I just picked some questions from the textbook to look at. All right, we're going to kind of go in the order of the chapter. Okay, so sometimes I'll put the questions up on in the presentation, or sometimes I'll just write the next question on my board to save some time. But we'll figure it out. So the first question says to express the equilibrium constant for the following chemical equation. Okay, and when we're expressing the equilibrium constant, we're going to take the products, divide them by the reactants, and then we're going to raise these values to whatever coefficients are in front of that particular product or reactant in our balanced equation. There's a little shorthand version of how we can note that. So in this case, these are our products. These are our reactants. I know it seems silly to even write this out at this point, but a lot of times when people are writing the KC expressions, I still do it sometimes when I'm doing out problems. So I accidentally switch them. Just, it happens. So if you label them, sometimes it happens less. So we know we want our products over our reactants. So our KC expression for this would be the concentration of the CO times the concentration of the H2 squared. And we'll put it over the concentration of CH3OH. Okay, so easy as that. The next example I have is for a slightly longer reaction. Okay, so this one is C3H8 plus 5O2 produces 3 CO2s and 4 H2Os. I mean, this one's a little more fun, at least, to write because there are more coefficients involved here. So to write the KC for this, we'll do the products first. Okay, so CO2 raised to the third times H2O raised to the fourth over C3H8. And we don't have to raise that to anything. It's like raised to the 1. And then O2 raised to the 5th. All right. Okay. The next question, I'll put this one up on the board so you guys can look at it, or on the screen rather. The next question we're going to look at gives us an overall equation. Let me find my little laser pointer. So it's giving us this overall equation and a corresponding K value. And then it's asking us to find the equilibrium constant for this reaction, which is kind of a manipulated version of the equation they gave us initially. So whatever changes that we make to this reaction to get from this point to this point, we have to take care to make the appropriate changes to the K value that goes along with it. All right, so that's what we're going to work on here. Okay, we have a K value of 5.6 times 10 to the positive 5. So to get to this reaction, the new version of this reaction, this one is NH3 yields 1/2 N2 plus 3/2 H2. So we have to ask ourselves, how did this reaction change? Okay, and two things should stand out, right? One is we reverse the reaction. And the second is that we have halved this initial reaction. Okay, so we divided it by 2 or multiplied it by a half, whatever you want to say. So we have to change K in a way that matches these changes. Okay, so when we reverse a reaction, that affects K. Well, I said that weird. When we reverse a reaction, we're going to take the inverse of the K value, and that's going to represent our new K for this reaction, K prime, we can call it. Okay, so we're going to take the inverse. Okay, when we multiply or divide a reaction, it's actually easier when we're working with K to think about the changes, whether they're multiplication or division, to represent them as a multiplier instead of something that's divided. Okay, and that's because you want to raise you want to use that multiplier as a coefficient and raise K to that. Okay, so if we say, for example, that we took this reaction here, we divided every coefficient by 2, or we multiplied the reaction by 1/2, we're going to take this value that we multiplied the reaction by, and then we're going to raise our K value to this exponent. Okay, so it's a lot easier to think about what to do in this step with your K value if if you're talking about multiplication versus division here. So you're like, all right, Lauren, let's get to the point here. What do we do with K? So our K value was 5.6 times 10 to the positive 5. So the first thing I'm going to do is I'm going to take the inverse of that. So that'll be represented as 1 over 5.6 times 10 to the 5. Okay, and then I'm going to take this value and I'm going to raise it to 1/2. And that's going to be my new K value. All right, now when you throw this into your calculator, and I would recommend trying it out, because when you have these exponents that are on the bottom of the fractions and you're raising things to fractions, sometimes the calculator work there gets a little bit complicated. So you should be able to calculate this out to 1.3 times 10 to the negative 3. Okay. All right, let's take a look at the next question. Okay, so this is very similar. We're looking at one equation, we're going to change it a little bit, and then we're going to see how that changes K. So we start off with the reaction 2COF2 gives me 1 CO2 and then CF4. Okay, and then my new reaction that I'm looking at is 2 CO2 plus 2 CF4 produces 4 COF2. Okay, and I want to find this K prime value. All right, so again, I'm going to go through and I'm going to list the changes that happened. I see that my COF2 went from a reactant to a product. So I know that the reaction's been reversed, which means I'm going to be taking the inverse. And I've also multiplied this entire first reaction by 2. So I'm going to have to raise to the multiplier. That's what we can call it. And in this case, that multiplier is going to be 2. All right, so I take my original K value, take the inverse of it, and in this case, I'm going to square it because my multiplier was 2. Okay, and we get 2.1 times 10 to the negative 13 as our new K value. All right. The next one is even more interesting. I say interesting. I'm just going to assume that y'all agree with me. People look at this one and they're like, all right, I kind of get this. It should remind you a little bit of Hess's law. We're going to go through that same first kind of process where we're going to be looking at how we manipulate these two reactions in order to get this one back out. Okay, and then whatever changes that we've made here, we have to kind of reflect them in the K values, and then we'll go over how we calculate the overall K from that. But our first steps are going to be to, to get this overall reaction back out from these reactions. So let me write this stuff down. Okay, so I'm just rewrote this. I'm just going to call this first little reaction or baby reaction, whatever you want to call it, 1, and I'm going to call its corresponding K value K1. Doesn't really matter what you call these, as long as you know which K refers to which reaction. And I'll call this K overall. Okay, so I have to see how I can manipulate these two reactions so I get my overall reaction back out. Just like in Hess's law, I think the easiest way to do that is to make sure that your reactants and your products are on the correct side first and start from there. So when I'm looking at this first reaction, I see that I have carbon dioxide on the reactant side here, but carbon dioxide is on the product side of this baby reaction. So I know right away that I need to reverse this. All right, so before I do anything else, I'm going to reverse this reaction and then see what it leaves me with. So I have CO2 and H2 on the reactant side now, and CO gas and H2O on the product side. Okay, I'm going to cross this out just so I don't confuse myself. And now I'm going to look at these two reactions. Now, when I reverse this reaction, I have to remember that my new K value is going to be, my new K1 value is going to be 1 divided by 1.0 times 10 to the 5. Because I reverse this, and when you reverse it, you have to take the inverse of K. All right, so this isn't my K value anymore. This is my new K value. All right, now when I look at the sum of these two reactions, I'm going to see if I get my overall reaction back out, because all my reactants and products are in the right place for this now. All right, so I can see right away that I have carbon monoxide on the product side here and on the reactant side here. So I can cross these out. I see that I have two H2s in my second reaction and one H2 in my first reaction. They're both on the reactant side, so I'm going to sum them together. Okay, I have one CO2 over here, so I'll bring that down. And then what's left on my product side is the CH3OH and the H2O. Okay, everything that's in this reaction matches the overall reaction I was looking for. So I know that the change that I made was appropriate. It was what it was supposed to be. So now I have to find my K overall. Okay, and to find your K overall, you're going to look at the K values that you have here, and you're going to multiply them. So it's going to be K1 times K2. And make sure that these K1 and K2 values that you're using reflect any changes you made to the reaction. So right after we reverse this reaction, right away, we altered the K value. So we've already done that step, okay? So our K overall is going to be 1 over 1 times 10 to the 5 times 1.4 times 10 to the 7. Okay, so we just got to plug that into the calculator. Okay, we end up with 1.4 times 10 to the 2. It's our overall K value for this reaction. Okay. Oh, everything comes back, right? Thought Hess's law was done. No way. It just, it just modified itself a little bit, took on a little different form. Okay. Now let's take a look at relating Kp and Kc. Okay, so we have this overall reaction. It's important to write down the overall reactions and to pay attention to the overall reactions when you're looking at the difference between Kp and Kc, because the moles of gas on each side of the reaction play a big part in this calculation. Okay, and our Kp here is going to be 2.2 times 10 to the 12 at 25 degrees Celsius. You'll also know that notice that the temperature is given here because that plays a role in the conversion from Kp to Kc and vice versa. All right. So we wrote down our info. So let's take a look at our equation. I think your textbook gives you this equation for Kp. And I want to look at it a little bit before we solve it anyway. So it's Kc RT raised to the delta N. Okay. Obviously, you're going to be given one of these two values to start with, right? Either your Kp or your Kc, and you'll be finding the other one. This R value here, back to your gas law, your ideal gas law constant. That's what we're looking at here. 0.0826. Okay. I'm writing out these units because I want you to see, right? Moles over Kelvin, that temperature there. That means that this temperature value has to be a temperature value in Kelvin. Okay, it can't be temperature in Celsius, it can't be temperature in Fahrenheit. The other thing that we want to pay attention to here is what this delta N value means, right? I've seen a lot of confusion about this in the last couple weeks. So when we're looking at the delta N value, this is going to relate to the balanced chemical equation. I told you that this relates back to your balanced chemical equation. This is where that happens. Delta N is going to be the moles of your product gas minus the moles of your reactant gas. And you're going to look at the coefficients of the balanced equation and the states of your reactants and products to figure this out. So if we're looking at this overall reaction, we see that when we look on the product side, we have 2 moles of NO2 gas. So the moles of our product gas is 2. When we look at our reactant side, we see that there's 2 moles of NO gas and 1 mole of O2 gas. 2 plus 1 is 3. So that's 3 moles of reactant gas overall. So our delta N value in this case is going to be 2 minus 3 or -1. Okay. Really important that we do this correctly because, the delta N value for these Kp and Kc equations, they could be negative numbers or positive numbers. So you have to make sure that you're putting the right thing in the right place so that you get the correct exponent that you're looking for. Okay. But we have all of that. Okay. In this case, we have Kp and we're solving for Kc. So we're going to reorient this equation a little bit so that we're solving it for Kc. So that'll be Kp over RT raised to the delta N. Okay, now we can plug in all these things that we know. So let's erase some of this. We know that Kp is 2.2 times 10 to the 12. We know that 25 degrees Celsius, if we add 273 to that, we'll have 298 Kelvin. Also notice that we're going to be keeping this R and this T value inside of a parentheses. Make sure that you multiply the R and T together before you raise it to the exponent. I'm leaving out the units here for space. And then we're going to raise it to this delta N, this -1. Okay, and again, practice putting this in your calculator. Make sure you get the right thing back out. Okay, when you plug this into your calculator, you should end up with a Kc value of 5.4 times 10 to the 13. Okay. All right, let's look at another one. We'll go in the opposite direction this time. This time they gave us the Kc value and we'll find the Kp value. Okay. So we have all the info that we need. We'll go back to our formula. Here we're finding Kp. Okay, so we just have to kind of sort everything out. We know that our temperature is 25 degrees Celsius. It's going to be 298 Kelvin. Our delta N value, 2 moles of gas here, minus 1, 2 moles of gas here, right? So we have a delta N value of 0. This is important because I want to show you something that happens here. So now we're going to go and we're going to plug this in to find our Kp value. It's going to be 6.2 times 10 to the 2. Okay, and then we're going to multiply 0.08206. Again, I'm just going to forego the units here for space. So we multiply R and T and then we raise it to the 0. What happens, and you can try this in your calculator right now, when you raise something to the 0, Anything raised to the 0 is going to be 1, right? So whenever we have an equal number of moles of our product our product gas and our reactant gas, our delta N value is going to be 0. And when our delta N value is 0, our Kp equals our Kc. Okay, this is true when our moles of product gas equals our moles of reactant gas. All right, you know, it's very exciting stuff. Riveting, I would say. All right, let's take a look at this. So the next example has us looking at equilibrium constants for mixed reactions or heterogeneous reactions. Forget how your textbook phrases it. But reactions where you're going to find solids or liquids as part of the reaction, because we don't treat those the same way when we're looking at equilibrium constants. Okay. So the rule of thumb when you're dealing with solids or pure liquids, and if you know it was a pure liquid because instead of an S, there would be an L here. When you're dealing with pure solids or pure liquids, they're replaced in your Kc expression with the number 1. Okay. So when you're asked to write an equilibrium expression for this reaction, products over the reactants raised to the coefficients, you're not going to include CaO solid. If you want, you can put 1 in as a placeholder. You still include the concentration of the CO2 gas though. Okay, and you would raise it to any coefficients that were present. None in this case. And then you're going to divide it by the reactants, which is in this case is CaCO3, a solid. So again, I like to put a placeholder of 1 there. I don't like to say that you would just drop it out completely because sometimes people get confused with what that means. So in this case, the Kc for this reaction would be just, let me rewrite it like this. Kc equals the concentration of the CO2. All right. But this is what I'm talking about though. Like say that I was looking at the other direction of the reaction. Say I was looking at CaO solid plus CO2 gas, CaCO3. And I wanted the Kc of this reaction. If I don't remember to substitute a 1 in for my solids, I'm going to end up with a really confusing equilibrium constant for this. Okay, because it's products over the reactants raised to the coefficients. But in this case, the only product I have is a solid. Okay, I have to represent that in this case as a 1. On the bottom of the fraction bar, that's where my reactants go. Okay, so even though I don't have to include the CaO, which is a solid, my Kc expression has to represent this carbon dioxide concentration as being on the bottom of the fraction bar. So the Kc for this reaction in this direction is 1 over the concentration of CO2. All right, that's why I think it's easier when you see the solids or the liquids in there to at least substitute the 1s in initially so that you don't forget to move something to the bottom of the fraction bar if it needs to be there. Okay. Let's look at one that involves a liquid. So this reaction. All right. So here again, products over the reactants, raised to the coefficients. Okay, these are our products, these are our reactants. So we're going to, again, substitute the H2O with a 1, and then we'll have our concentration of Cl2 squared. And then we'll divide it by the HCl raised to the 4th times O2. And then you can simplify it and you can take out the 1. Okay, easy as that. We haven't done any math so far in these, so let's take a look at a couple of math questions. We'll share this. You can write down the reaction. I saw some of you at my ice table workshop, so you are already familiar with my method for solving these equilibrium problems. But for those of you who missed it, I'll show you what I like to do. Okay, so this question tells us that a reaction mixture at 780 degrees Celsius, and they're telling us the temperature here because remember that the equilibrium constants are temperature dependent. So they have to really specify that it's at a particular temperature. It initially contains a concentration of CO of 0.5 and a concentration of H2 of 1 molar. And then it says at equilibrium, the CO concentration is found to be 0.15 molar. What is the value of the equilibrium constant? So they gave us a lot of information to work with here to calculate this equilibrium constant. And we're going to organize the information using this ice table, right? Don't be intimidated by the ice table. It's really just a way for you to organize your information. Okay, so you start with this initial row and you fill in whatever you can. I like to draw a really thick line between my reactant side and product side just so I can like visually recognize where the split in my reaction is. They told us that we're starting with 0.5 molar CO and 1 molar H2. Okay, they also told us that at equilibrium, and actually let's take a minute just to make sure that we all know what these rows stand for. The I in the ice table stands for the initial amount. The C stands for the change that happens. And then the E stands for the equilibrium value. Okay. You are trying to find the equilibrium value for each of these things because these are the values that you have to use in order to calculate Kc. Kc can only be calculated from equilibrium values. All right. So they tell us that at equilibrium, the CO concentration is found to be 0.15 molar. Okay. In this chapter, you are asking yourself quite frequently, which direction is this reaction going? Okay. This is another example of you having to be able to like intuit the direction of the reaction from the information that you're given here. All right. You started out with 0.5 molar CO. In the end, you were left with 0.15 molar CO. That means that over the course of the reaction, you were using up your CO and you were making CH3OH, right? Hopefully that makes sense. Also, your initial concentration of the CH3OH was 0 molar, right? They didn't give us that initial amount there. They were telling us we started with this, which means that we're making this. Okay. Now, the reason I went through trying to point out what the direction of the reaction was, because this tells us what our change expression is going to be, or yeah, kind of like, I guess that's the right way to say it, what our change expression is going to be. This change row, you see in your textbook, it's represented with minus and positive x values, negative and positive x values. You decide whether the X values are going to be positive and negative based on whether they're on the reactant side of this arrow that you drew or the product side. Okay. Or if you want to think about it like this, I started with 0.5 molar CO. I used up a bunch and it decreased to 0.15, right? So the fact that I went from 0.5 to 0.15 means that I decreased my amount, so it gets a negative sign. All right. Now, hydrogen gas and carbon dioxide gas are on the same side of the reaction. So if I'm using up carbon monoxide, I'm also using up my hydrogen gas. So I'm using these two things up and I'm creating the CH3OH. So whatever you're using up gets a minus sign. Whatever you're making gets a positive sign. Okay. We don't always know the change value, so we represent it with an X. But if there is a coefficient in the equation, that coefficient goes before the X value. CO does not have a coefficient there, so we can just say it's 1X. You don't have to put that 1 in there. I'm just doing it for demo right now. The change for the H2 is going to be minus 2X. And the change for CH3OH will be plus 1X. All right. And then the value of this equilibrium row we get from combining these two rows. Okay. So we can represent the equilibrium value for H2 as 1.00 molar minus 2X. For CH3OH, it'll be 0 molar plus X. All right. Now, they gave us enough information in this problem so that we can figure out what this X value is, what this change is, because they told us what the equilibrium concentration for the CO is. We know that when we take the 0.5 molar initial concentration and we remove X from it, that we're going to end up with 0.15 molar, right? So we should be able to find what that X value was, what that change value was. Okay, so we get 0.35 molar is going to be our X value. Once we have that X value, now we're going to go back to our equilibrium row and we're going to plug in 0.35 molar everywhere that we had an X value. Okay, I'll make this equilibrium, these two boxes, I'll make them a little bit longer so we can solve this out for numbers. Okay, so if we have 1 molar minus 2 times 0.35 molar, we're going to be left with 0.30 molar. 0 molar plus 0.35 molar is going to be 0.35 molar. Okay, and we were already given this concentration. So now we have our 3 equilibrium concentrations. Now we can solve for Kc. All right. And our Kc expression for this, products over the reactants raised to the coefficients. So CH3OH divided by CO divided by H2 squared. So we have 0.35 divided by 0.15 divided by 0.30 squared. Again, put this in your calculator. Don't just say, yep, got it, and keep on going. When you calculate this out, you should get a value of 26. Okay. Let's look at another one that's similar. Let's say that we have the same reaction. Okay. and we have a different temperature. We're going to carry this reaction out at a different temperature now, so our K value is going to change. And this time we have an initial concentrations. Sorry, I have to make my ice table first so I can fill this in. I always make my ice table right underneath my formula, right underneath my equation, because then I'm like, it's already labeled for me. So initial concentration of CO of 0.27 molar. H2 will be 0.49 molar. Okay, and we can fill a 0 in for the CH3OH. And at equilibrium, the concentration of the CH3OH is 0.11 molar. Let me just show you the question in case you want to write down. You can pause it and like write it down properly. Okay, but that's what I'm working with here. Okay, but this is the main information that I pulled out of it. Now, again, we can tell that we could tell the direction of the reaction based on the numbers here. We went from 0 CH3OH to having 0.11 molar. So that means that we're creating methanol, right? We're adding it, we're making it. That's a plus sign. If we're making the CH3OH, that means that we have to be using the CO and the H2 gas up to make this. Okay, if we're using them up, they're going to get minus signs. Okay, and then those X values are going to be put in there, including the coefficients if they're applicable. Okay, and this time we're figuring out the X value based on this information here. Okay, so we can tell that if 0 plus 11 or 0 plus X equals 0.11 molar, then we see that our X value in this case is 0.11 molar. So everywhere that we see an X, we can plug in 0.11 molar. See, notice that I plug it in for the X, but I leave the 2 alone. So now when we want to find the equilibrium concentrations of these two things, we just combine these 2 rows. So to find it for CO, it's going to be 0.27 minus 0.11. For our H2, it's going to be 0.49 minus 0.22. Okay. Once we have all 3 equilibrium concentrations, remember we have to use that E row to find Kc. We're going to do our products over the reactants raised to our coefficients. Okay, so 0.11 over 0.16 over 0.27 squared. And we get 9.4, 2 sig figs. So that's our Kc here, 9.4. Okay. All right. Let's try another one. Okay, so we're going to write down the reaction first and let that be your guidepost. Okay, and then we'll set up the structure of our ice table here. Okay, so this problem tells us that we have a reaction mixture at 1700 degrees Celsius. It initially contains just some CH4 at 0.115 molar. At equilibrium, the reaction mixture contains 0.035 molar C2H2, and we're going to find the Kc value from this. Okay, so we know right away that we started with none of these products. Okay, the next thing that we can do in this case is we can fill in this change row. We know that we're creating C2H2, so this is going to have a positive sign. If we're creating C2H2, that means we're also creating the H2. And to create these things, we're using up our CH4. Okay, so now plug in your X values with their proper coefficients. So this will be minus 2X for CH4, plus X for C2H2, and plus 3X for H2. Okay, and in this case, they again very nicely gave us an easy X to solve for here. Because when we look at these two rows here, 0 molar plus X is going to equal 0.035 molar. That means that our X value equals 0.035 molar. So everywhere where there's an X in our change row, we can substitute that in with 0.035 molar now. So we'll substitute that in over here and over here. And now we'll combine everything and we'll find our equilibrium concentrations. Okay, so notice how we decreased in amount here. We have that one. Okay, and these are our equilibrium values that we're going to use to solve for Kc here. Okay, so let's write out our Kc expression first. Products over the reactants raised to the coefficients. We have C2H2 times H2 raised to the third divided by CH4 raised to the second. Okay, now we can plug in the numbers. 0.035 times 0.105 raised to the third divided by 0.045 squared. Okay, and our Kc value here equals 2, yeah, we'll say 2.0 times 10 to the negative 2. All right, so the next question still has us looking at this same equation. We're just changing around, the starting material again. So the reaction of CH4 in the previous example is carried out at a different temperature, so the Kc is going to change, with an initial concentration of CH4 of 0.087 molar. At equilibrium, the concentration of H2 is 0.012 molar. Find the equilibrium concentration at this temperature. Okay, so we're going to proceed pretty much the same way that we did before. We know that we're starting with CH4, and we're not going to be starting with any of the other reactants. Okay, and we know that we're creating the H2 gas. And if we're creating the H2 gas, that means we're going to be using a plus sign to indicate our change here, right? And if we're creating the H2 gas, that means we're using up the CH4. Okay, so now we have to find the value of X using these pieces of information here. So we know that 0.00 plus 3x is going to equal this equilibrium value of 0.012. Okay, so that means that we could say that 3x equals 0.012. Okay, so there's our x value. So we're going to plug this in now for these x's, and we're going to solve for our equilibrium. Okay, so this will be 0.004. This will be 0.079. Okay, and these are equilibrium concentrations that we can use to solve for Kc now. All right, so our Kc value is going to be products over the reactants raised to the coefficients. Okay, and we're just going to plug in these equilibrium values now. Okay, and we'll calculate our Kc. And we get a very small value, 1.1 times 10 to the negative 6. Okay, so whatever that temperature was, it decreased our Kc value by a lot. All right, let's look at our next question. So here we're going to be looking at this Q value. We're going to start to see how we can use Q to help us interpret our equilibrium reactions. We can use it to tell whether a reaction is at equilibrium. It's pretty helpful. So here we're looking I2, Cl2. Okay, and our Kp here is 81.9. Okay, so there's our reaction, our Kp value. And they're giving us information that says a reaction mixture contains Pressure of I2 of 0.114 atm, pressure of Cl2 of 0.102 atm, and a pressure of ICl of 0.355 atm. Is the reaction mixture at equilibrium? If not, what direction will the reaction proceed? Okay, so I've gotten a lot of questions recently about like just what is the point of Q? Like what is Q? What do I do with it? Q is a way to figure out like where your reaction is at. Okay, is my reaction going to go in the forward direction? Is my reaction going to go in the reverse direction? Like it's helping you predict the direction of that reaction, right? So what does that help you predict? It helps you predict whether you're going to be creating more products or whether you're going to be creating more reactants. Because if it's a forward direction that's being favored, then your products are being favored. If the reverse reaction is being favored, then your reactants are being favored. Okay, and we can compare our Q values to our K values to help us figure this out. All right, the first thing to realize is that when your Q value is equal to your K value, this is the point where your reaction is at equilibrium. Okay, when your Q is equal to your K. When your Q is not equal to your K, your reaction is going to change so that the values of the reaction, so that ratio of products to the reactants, so that ratio equals the K value. Okay, it's whatever is happening in your reaction, the reaction is trying to get back into position, so the ratio of products over reactants raised to the coefficients is equal to this K value that you're given over here. All right. Another thing that I want to mention, since this is I think it's the first time we've seen it in this series of questions, is we're given pressures to use. Okay. When we're given pressure values to use, that is when we're looking at the Kp expression as opposed to the Kc expression. When we're looking at pressures, we have Kp. When we're looking at concentrations, that's when we're looking at Kc. Right? Now, when you're looking at Kp, then you're going to use the Qp expression to compare it to. All right, but it doesn't really matter what that little subscript is after the K or after the Q. What matters are pretty much the numbers, right? That's what's going to give us, that's what's going to tell us what's important here. So we're going to set up our Q expression the same way we would set up our K expression. So to find our Q using the pressures, it's going to be products over the reactants raised to the coefficients. Okay, so the pressure of our ICl squared divided by the pressure of our I2 times the pressure of our Cl2. Okay, so that's the first thing we'll do is we'll plug in these pressures and we'll get a value of Q back out. Okay, so I get a value here of 10.8. Okay, so in this case, I'm gonna write over here. My Q is 10.8. My K value is 81.9. They told me this at the beginning of the question. So in this case, my Q value is less than my K value. All right. When your Q value is less than your K value, your reaction is going to proceed in the forward direction. Okay. Your reaction is going to proceed in the forward direction, and it's going to try to create more products. Okay? Going to try to create more products. Why is that true? Because look back here at our K expression, or at our Q expression rather. Let me write this out over here. Well, I'll write it over here. So Q is, I'm going to write a simplified version of this, right? So Q is products over the reactants. So I want my Q value to equal this K value, right? This is my goal, is to get it to equal. That's when we're at equilibrium, when Q equals K. So if my Q value is too small, right? How can I make it bigger? I can make my numerator bigger, right? If my numerator gets bigger, then the whole number gets bigger. Well, my numerator can only get bigger if I make more products. So that means that the reaction has to go in the forward direction so I can make more products, so my Q value can get bigger, and it can eventually equal K. All right? If, on the other hand, if my Q was too small, okay, let's just draw a little thing over here. Let's say that my Q value, not that my Q value was too small, that my Q value was too big, say that my Q value was larger than K, right? Say that my Q value was 100 and my K was 81. Okay, I need my Q value to get smaller. So how can I make my Q value smaller? Well, I can make more reactant. If I increase the amount of reactant, then my denominator gets bigger. And when I divide these two things, my overall number, my Q value will get smaller. All right. So hopefully that explains the directionality of the shifting that's happening there. When my Q number is less than my K number, my reaction proceeds forward and makes more products because it's trying to make that Q value larger so it can match the K value. All right. All right. What now? Okay, we're gonna do some more Q calculations. Let's look at this one. Okay, and this one says a reaction mixture contains a concentration of 0.0255. I don't need that brackets. 0.0 molar NO2 and 0.0331 molar N2O4. We want to calculate QC and determine the direction in which the reaction will proceed. Okay, for us to do this comparison, we have to be given the K value to compare it to, because we can calculate Q with some initial concentrations. You can calculate Q at any point in the reaction. All right. Where with the equilibrium constant, you have to use equilibrium concentrations. That's not true for Q. For Q, you just need concentrations and you can calculate it. Or you just need pressures and you can calculate QP. When we call it K, that means that we're at equilibrium. Okay. So in this case, we're going to calculate QC. You'll notice that it's C because we're using concentrations again. And we're going to do the products over the reactants, raised to the coefficients. So it'll be NO2 squared over N2O4. Okay, so what's happening here? We have a Q of 1.96 times 10 to the negative 2. We have a K of 5.85 times 10 to the negative 3. Okay, in this case, our Q value is bigger and our K value is smaller. Okay, so what did we say in that last explanation? When our Q value is too large, we want to make the reaction, or we're not making the reaction do anything. When the Q value is too large, the reaction itself is going to shift to the left and try to produce or create more of this reactant. And as it creates more reactant, this Q value will get smaller and it will eventually be the same value as the K value. And that's what it wants. So in this case, the reaction proceeds left towards the reactants. Okay. All right, we got another different type of example now. So we have 2 COF2 and our Kc here is 2 at 1,000 degrees Celsius. Okay, so this says in an equilibrium mixture, the concentration of the COF2, so we're at equilibrium here, the concentration of the COF2 is 0.255 molar, and the concentration of CF is 0.118 molar. And it asks us, what is the equilibrium concentration of the CO2? Okay, so that's our unknown. I personally love questions like this because we can just do some algebra to sort it out. But you do have to know how to set it up before you can make that step. Okay, so the key here was that they told us that the mixture that we were looking at was at equilibrium already. So these values that they're giving us are equilibrium values. All right. We know that K is equal to products over the reactants raised to the coefficients. So let's just write out our Kc expression real quick. Okay, and now we can plug in the values that we know. And what do we know in this case? It's a little bit different. We know Kc, we know CF4, we know COF2, and we're going to solve for X. Let's plug in these values. We'll just see that as CO2. Okay, so now we're just going to do some algebra. Okay, so okay. I mean, you could rewrite this if you want to rewrite it like so that you're not just plugging it into your calculator. You know, you can multiply both sides by 0.255 squared over 0.118. Let me just want enough room to write it on both sides. You know what I mean? Like cancel this stuff out. And then you can like, you know, write it nicely as the concentration of CO2 is going to be equal to 2 times 0.255 squared over 0.118. Okay, I know sometimes people get a little bit jammed up with the algebra there. So when you plug that all in, you should get a concentration of 1.10 molar back out for your CO2 concentration. Okay, let's try another one like that. So I'm just writing down all the information. They're telling us that the initial concentration of I2 in this case is 0. Oh, not the initial. They're telling us that the equilibrium concentration, got to be careful with that. Equilibrium concentration is 0.10 molar. And we want to know what the equilibrium concentration of the I is. Okay. All right, so we're going to do that same setup. Kc equals products over the reactants raised to the coefficients. Okay, so we can actually, I'm going to just substitute this an x value in here, just because I like, solving for x in these things. So we'll have x squared divided by 0.10 molar, and that's going to equal 0.011. Okay, maybe I'll do this. All right, so I'm going to multiply both sides by 0.10. And then I'm going to take the square root of both sides. Okay, and I end up with an x value of 0.033 molar, and that's going to be the concentration of the I at equilibrium. Okay, hopefully that's pretty straightforward. Let's see. Okay, we'll do one more of these. One more. Oh, this one's even better, actually. It's not. I thought it was the same, but it's not. So this one says, we have a reaction mixture at 2000 degrees Celsius. They're giving us the Kc value here, so I'll write it over here. And it initially contains 0.2 molar N2 and 0.2 molar O2. Okay, and we're going to find the equilibrium concentrations of everything just based on this information here. Oof, these ones, man. Sorting them out initially can be a little frustrating, but they're not that bad. So we're going to start by filling in what we can fill in our ice table. So we're starting with N2 and O2. So we have a 0 over here for our NO. Okay. Now, we're not given equilibrium values to help us determine the direction of the reaction, but you can kind of reason it out with yourself if you want and say, well, if I'm starting with reactant and I have no product, my reaction is going to have to go this way so I can create some product. Okay. You can also substitute these concentration values into Q and solve for Q. In this case, our Q would equal 0 because our product is 0. If our Q is 0, then our reaction is going to proceed to the right, because our K is higher than 0. All right, so hopefully that makes sense. So we know our reaction is going to go in this direction, and we're going to be trying to form some of this NO gas. If we're trying to form some of the NO gas, it's going to have a positive change sign, and it'll be a positive 2x. We're going to be using this stuff up, so that's going to be minus x minus x. All right, so our equilibrium row is going to be, remember, we're combining the first two rows to get that equilibrium row. So our equilibrium for N2 is going to be 0.2 minus x. For oxygen, it's 0.2 minus x. And for NO, it's going to be 2x. Okay. Now we're going to set up our Kc expression using these numbers. Okay. So Kc is going to be products over the reactants raised to the coefficient. All right. And now we're going to plug in this row. So it's 2x squared over 0.200 minus x times 0.200 minus x. Okay. Now in this case, we have two values that are the same on the denominator, so we can rewrite this as 0.200 minus x squared. Okay, and this actually helps us out with solving this, because what we need to do is solve for x here so that we can find real values for these equilibrium concentrations. By rewriting this so that we have an exponent of 2 on the numerator and an exponent of 2 on the denominator, makes it a lot easier for us to solve for x, right? We know that this expression is going to be equal to our Kc value of 0.10. So now we can take the square root of both sides. And what the square root does on this side is it gets rid of these exponents. So now we just have, I'm going to rewrite it over here. We have 2x over 0.200 minus x equals 0.10. Oh, square root of 0.10. Let me get a number for that, because I'm going to forget that square root. Okay, 0.316, much better. I'll definitely forget to write that square root and be confused at the end. All right, so now we're going to be solving for x. So the first thing I'm going to do is I'm going to multiply both sides by 0.200 minus x. And I'm going to rewrite that. So 2x is going to equal, remember to distribute that 0.316. Okay, and now I'm going to add the x to this side. So I have x's on one side and not x's on the other side. Okay, now I'm just going to divide both sides by 2.316. so that I can isolate that X value. And my X is going to equal 0.0273. All right. Now, once we have this X value, now we're going to go back and we're going to plug it in everywhere that we have an X in that equilibrium row. We're going to go plug that X in. Okay. I'm going to erase a little bit of this math because I'm going to need a little extra room to write our numerical equilibrium values. Okay. So 0.200 minus 0.0273 is going to be 0.173 molar. This will also be 0.0173 molar because they're the same. Then 2 times 0.0273 will be 0.0546 molar. Okay, so these are our equilibrium concentrations. And you can double check this if you wanted to, because you can plug that back in to your Kc expression and you should get something very close. Don't worry, we're going to look at some quadratic ones shortly. Okay, let's look at one more example with the previous reaction. Here we have a different Kc value because we're at a different temperature. Okay, so our Kc here is going to be 0.055. And this time we are starting only with our NO. Okay, this doesn't really change anything when we're doing these calculations. It doesn't really matter where our starting material is. We just have to be able to understand which way the reaction goes when we have that particular starting material. So here they're telling us that we're starting only with 0.1 molar NO. And we're going to find the equilibrium concentrations of everything. Okay, and just like, just like we were talking about last time, if we're starting with 0.1 molar NO and we have no nitrogen or oxygen, then the NO is going to start to convert into nitrogen and oxygen. Okay, so it's going to decrease in concentration as it starts to form oxygen and form nitrogen. All right, that's why we have a minus sign over here with the NO and we have plus signs over here. Okay, so if we're starting with no nitrogen, no oxygen, then we have to be creating it. And if we start with our 0.1 molar NO, we have to be using it up. So our equilibrium row will be represented as 0.100 molar minus 2x. And this will be x, and this will be x. You write this a little bit higher, so last time I needed more room. Okay, so now we can set up our Kc expression, just like we did before. So 0.055 is going to equal products over the reactants raised to the coefficients. We still set up our Kc value the same way we did before. This Kc expression is true when nitrogen and oxygen are our reactants and NO is our products. Okay, so it's not like we're physically rewriting the reaction and we're going to take the inverse of K or anything like that. If we use this Kc value, then we have to label our NO as product and our our nitrogen, our oxygen as our reactants. All right. So we'll set this up as 0.100 minus 2x squared. That's our products. I guess we can call it the products in the written reaction, even though it happens that in this reaction mixture, the reaction is moving in the other direction. But as the reaction is written, this is our product and these are our reactants. Okay. So I'm going to rewrite that as x squared. I'm going to multiply it by both sides so I can get it out of that denominator. So I end up with 0.055 x squared. No, I guess I won't do that yet. So I'll take the square root first, just like we did before. So I'll rewrite that as x squared over here. And I'll take the square root of both sides before I start so I can get rid of these squares. But I gotta take that square root before I forget. Okay, so the square root of 0.055 is 0.235, and that'll be equal to 0.100 minus 2x over x. Okay, so now I'll multiply both sides by x. Just rewrite it like that. I will add 2x to both sides. And then I'll divide by 2.235. Okay, so this is our x value. Now we're going to substitute this value in everywhere it says x. All right, and that's going to give us our equilibrium concentrations. Okay, so it's pretty easy for us for the nitrogen and the oxygen because we just have to rewrite the value. Okay, and these will be our equilibrium concentrations for nitrogen and oxygen. And then for our NO gas, instead of that x, we'll multiply by 0.0447, and then we'll subtract from 0.1. Okay, so our equilibrium concentration here is 0.0106. Okay, and those are our three equilibrium concentrations. Okay, but sometimes we can't take the square root when we are solving out these problems. And that means that we're going to have to use a different method to solve for x. That different method is, unfortunately, the quadratic equation. Let's take a look at one of these examples. So let's write down our reaction and our K value. Okay, and here it tells us that our reaction mixture at 100 degrees Celsius initially contains 0.100 molar NO2. Find the equilibrium concentrations of everything at this temperature. Okay, so for our ice table, okay, just kind of like we saw last time, if we're starting with some NO2, that means we're going to be creating N2O4. So we don't have any N2O4 to start with. So we're going to be creating it. That's a plus. We're going to be using up our NO2 to create the N2O4. So that's a minus. So this will be minus 2x, and this will be plus x. So our equilibrium row for N2O4 will be x, and for NO2 is going to be 0.100 minus 2x. Okay. So when we write our Kc expression, just so we have it written down here for reference, it's going to be NO2 squared divided by N2O4. Okay, so that's what we're going to be working with. So I'm going to plug in the 0.36 for my Kc. Okay, and then I'm going to have my NO2 value squared divided by x, which is my N2O4 value. All right, so we have to do two things right away to solve for this. We have to kind of, is it called foiling when you have to, you know, we have to solve this out, this squared expression out. And we have to multiply both sides by x so we can get x out of this denominator. Okay, so I'm going to multiply this by x. And I'm going to, I like to rewrite it, especially when we're first doing it so we can like see it. Okay, so I'm going to just get rid of that because I moved it over here. And now we're going to do 0.100 times 0.100, 0.100 minus 2x, minus 2x times 0.100, minus 2x times minus 2x. Right. We end up with 0.0100 minus 0.400x plus 4x squared. That's what this expression gives us. Okay, so let's rewrite that, something that's a little less messy. So we have x times 0.36, or 0.36x equals 0.0100 minus 0.400x plus 4x squared. Okay, hopefully that's good for everyone. I'm gonna erase this part so we can write a few more notes down over here. What this is setting us up for is solving for the quadratic. And remember that for the quadratic, we need three variables, a, b, and c. Our a variable is going to correspond to our x squared value. Our b value is going to correspond to our x value. And our c value is going to correspond to the number that has no variable attached to it. All right, so what we're going to do is we're going to take this expression and we're going to solve it for 0. And the numbers that we get back out, those are the numbers we're going to use for a, b, and c. All right, so to solve this for 0, I'm going to subtract 0.36x from both sides. Okay, and I'm going to rewrite this so that my x squared comes first, my x comes second, and my c comes third, but it doesn't change the numerical value of anything here. All right, so this is going to be 0, and then I'm going to write my 4x squared first. Negative 0.4x minus 0.36x is going to be negative 0.76x. And then I'm going to have plus 0.100. Okay, so this is the expression that I'm going to use to get my a, b, and c values. So my a here is going to equal 4. My b is going to equal negative 0.76. You have to keep the signs with it. Don't do what I just almost did. and my C value is going to be 0.100. All right. Once we have our A, B, and C values, now we are going to plug it into the quadratic equation. Okay, so our quadratic equation is minus B plus or minus B squared minus, square root, hold on. That's under a square root. B squared minus 4AC. And then everything is going to be divided by 2A. Okay, you're just going to plug your values in and then solve for the quadratic. So I'll make a little arrow and plug stuff in. So I'm going to have minus 0.76 plus or minus the square root of minus 0.76 squared minus 4 times 0.1 all over 2 times 4. Okay, now what I like to do is put this expression, including the square root, into my calculator and get a number for that, and then figure out what my positive and negative values are. Okay, because we're going to end up with 2 values for x because we have a plus and a minus right here. Right? So I'm going to rewrite my more simplified version of this here. So I have 0.76 plus or minus, let me put this mess into my calculator. So I'm going to do 0.76 negative squared, okay, and then minus, and then in parentheses I'm putting 4 times 0.1, close parentheses. Sorry, I messed that up because I forgot a 0. That's 0.01. So let me try that again. 0.76 negative squared minus parentheses 4 times 0.01. Okay, so I get 0.41476, and then I'm going to hit the square root key. And this value that I get is what I'm going to put right next to my plus or minus over here. So 0.6462. Okay, and we're going to divide that by 8. So now we're going to have like 2 versions of this. We're going to call it the positive version of x and the negative version of x. Okay, so solve for both of them and you'll get your positive values and your plus x value and your minus x value. Okay, so we have 0.176 equals x, and we have 0.0142 equals x. All right, and now you might be asking yourself, well, how do I know which x value is the right x value? Okay, the key here to remember is that I can write it down here, you can't have negative concentration values. So what that means for you is that if either of these x values that you calculated gives you a negative concentration when you plug it into your equilibrium row, then it can't be a good answer. It can't be the right answer, okay, because you can't have negative concentrations. So if I look at this first choice, my 0.176, I'm going to try to solve it for this expression here, okay? So this expression says 0.100 molar minus 2x. All right, so instead of x, I'm going to substitute in 0.176. What does that give me? Gives me negative 0.252 molar. Okay. I can't have negative concentrations. That means that this value is not the correct X value. It must be the other one. There will only ever be one answer that is correct when you're looking at these quadratics. Okay. Once you figure out which value is the correct value, you're going to plug that in for your X. So this will be 0.0142 molar. And now we'll solve for this one. Okay. And we get 0.0716 molar. And these are our two equilibrium concentrations. All right. I know, very fun, very exciting. So this time we're going to use the same reaction, but we're going to look at a different temperature, right? Because oh no, we're looking at the same temperature now because they're going to let us use the same Kc value. Okay, let me show you the question. So it says the reaction in the previous examples carried out at the same temperature, which means that we're not going to change the Kc value. But this time the reaction mixture initially contains only the reactant N2O4. Find the equilibrium concentrations. Okay, so we're going to see a lot of similar steps here. Okay, this time we have N2O4 to start with. We have 0.0250 molar. We have no NO2 to start with. So we're going to be creating NO2. So we'll say this will be plus 2x. And we're going to be using up our N2O4. So this will be minus x. All right, so when we look at our equilibrium row here, that's going to be 0.0250 minus x. And this is going to be 2x. Okay, so now we're going to plug this equilibrium row into our Kc expression. I can plug in the 0.36. Okay, so our NO2 value is 2x, so that's going to be 2x squared over 0.0250 minus x. All right, again, we can't get rid of the squares with a square root in this case because we only have the exponent on the top of the fraction. It would need to be on both the top and bottom of the fraction bar. So instead, we're going to solve this for 0 and use the quadratic equation. Okay, but we can simplify this a little bit first. We can change 2x squared into 4x squared. All right, and I'm going to multiply both sides by 0.250 minus x. I'm multiplying this side by it too, but I'm not going to write it down. Okay, so let's see what we get. 0.0250. Okay, so we get 0.009 minus 0.36x equals 4x squared. Okay, and I'm going to move these values to the opposite side. So I can move everything onto one side and make everything equal to 0. So plus 36x plus 0.36x minus 0.009 minus 0.009. Okay, and I'm going to rewrite my equation. So I end up with 0 equals 4x squared plus 0.36x minus 0.009. And my A is going to be 4, my B is going to be 0.36, and my C is going to be negative 0.009. All right, so let's plug stuff in. Write down our quadratic. Okay. Square root. Okay, let me just double check that. I like it way better when you guys are working these problems along with me so that you can check when I make silly calculator errors. Okay, I got that answer again. So now we're going to calculate the plus value and the minus value for this. Okay, so I'll note them like this over here. So we end up with x equals 0.11 or x equals negative 0.02. Okay, we can't have negative concentration values. So right away, this one's even easier because when you get a negative x value, you're going to immediately discard it. Totally useless to you. All right. So last step is to plug this x value in to your equilibrium row. So here we'll have 2 times 0.11. So we'll end up with 0.22 molar. And this will be point. Man, did I mess up me and my calculator? I tell you. Oh. Well, I think I made a little 0 mistake somewhere in here, and that's why this didn't work out. So that's my bad. I would go back and try to correct it right now, but I'm gonna confuse you guys more. You can try though. Wait, let me pause it and see if I can find the mistake real quick. I mean, I think I see it. I think I just forgot this negative sign. Life. Okay, so we're going to recalculate these. This is a good, actually, It's a good life lesson because when you calculate these x values and you go to plug it into your equilibrium row, if you end up with if nothing gives you a positive concentration, then you probably made a mistake in your quadratic. So you can go back and fix it like I just did. Yeah, so I forgot this negative sign here when I went from here to here. So that's definitely going to change my values. So again, we'll do a positive x and a negative x, right? I'm doing this one for when I add and this one for when I subtract. But I'm going to get a smaller number now because I'm starting with 0.36 negative. So now I get x equals 0.020, 0.0204. And this one's still going to be negative, but I like to calculate it just because. Okay. So I'm going to go back in there and fix these little x's that I had. So here I've got 2 times 0.0204. I end up with 0.0408 molar. And then for my 0.250 minus x, I'll be subtracting 0.0204. And I end up with 0.0046 molar as my equilibrium concentration. Okay. And those values make sense. Positive numbers, that's what we want to see. Okay. So maybe it's a mistake that worked out for the best because we got to talk about that. All right. What are we going to look at now? Now we're going to look at, what's this saying? Finding equilibrium partial pressures. When you're given the equilibrium constant and initial partial pressures. Sounds very exciting. All right, so take a look at this. You can write down the information if you want. Okay, and this is at 25 degrees Celsius. All right, so here, oh, this one's nice and this one's interesting. So our initial pressures here, call it IP since we're dealing with pressures. Not that you really have to. But we have 0.1 ATM of the iodine. Oh, we have 0.1 of everything. Okay. Okay, that's our starting. Now for this one, there is no clear answer here as to which direction this reaction is going. In the last few examples that we looked at, we can tell the direction of the reaction because we didn't have one of the reactants. So we knew which direction the reaction was going, right? Here, we're going to have to use our Q value to figure out which direction the reaction is going. So before I finish making my ice chart, I am going to look at this and calculate Q to figure out which way my reaction is proceeding. Is it proceeding towards the products and making more products, or is it going to be trying to make more reactants, right? So to calculate Q, I'm going to do the products over the reactants raised to the coefficients. So it'll be the pressure of ICL squared over the pressure of I2 times the pressure of Cl2. Okay, so that gives me 0.1 squared over 0.1 times 0.1, which is 0.1 squared. Okay, so we see here that in this case, Q is equal to 1. So if Q equals 1 and K equals 81.9, that means that Q is less than K. And remember, when Q is less than K, we're going to try to create more product so we can raise the value of Q. So our reaction is going to proceed in the forward direction towards the creation of more product. Okay, it's important for us to do that because remember, we're trying to figure out what's being used up and what's being created. Right? That's that change row in our ICE table that we have to focus on. So we can't do the change part of it if we don't know what's being used up and we don't know what's being created. Now, in this case, once we do that calculation, now we know that we're using up our iodine gas and our chlorine gas, right? So these get our minus X's. And we know that we're creating the ICL gas. We're creating more product. So that'll be a plus 2X. And our equilibrium value here will be 0.100 minus X, 0.100 minus X, and 0.100 plus 2X. Okay. And now we will use our KP expression, just like we were looking at before. We can write the formula version of it out over here. So KP is going to be the pressure of ICL squared over the pressure of I2 times the pressure of Cl2. Okay, so our KP is 81.9. That's going to be equal to this value squared. So 0.100 minus 2x squared divided by 0.100 minus x divided by 0.100 minus x. Okay, I'm going to rewrite this since these are the same thing. I'm going to rewrite this expression as 0.100 minus x squared, which, you know, that's like a relief to see that because it means that we don't have to do the quadratic. It means we can take the square root of both sides and get rid of these exponents, right? So I'll take the square root of this, take the square root of this, which will let me get rid of these. So let's rewrite what we have. 81.9 square root. That'll be 9.05. That's going to equal 0.100 minus 2x over 0.100 minus x. Okay, so now this looks more like algebra. So we have to solve this algebraically. I am going to multiply both sides by my denominator so I can get rid of that denominator. Okay, so I'm going to multiply this side by 0.100 minus x. I'm going to multiply this side, keep on moving this over. I'm also going to multiply this side by 0.100 minus x. Okay, so I'm just going to like distribute that in there. Okay, now I'm going to rewrite that so it looks like something I can actually work with mathematically. Okay, so times 0.1. So we're going to end up with, draw the line there, 0.905 minus 9.05x equals 0.100 minus 2x. Okay. The next step that I want to take is I want to put my x's on one side and my not x's on the other side, right? Oh shoot, wait, hold on. Before I do that, this is supposed to be a plus and this is supposed to be a plus before I really screw up this math. That was a plus, that was the ICL value over here. So that should have been a positive sign in there. Okay, so I'm going to combine. I'm going to move my 9.05x to the right side, and I'm going to move my 0.1 over here. And I'm going to minus this. And let's rewrite that. So this will be 0.805 equals 9 plus 2 is 11.05x. I'm going to divide both sides by 11.05. Okay, so my x value is going to be 0.0729. Okay, now this is a value I have to go and plug back in up here. All right, so my equilibrium value is going to be 0.100 minus 0.0729 for my iodine and my chlorine. And again, it's minus because I'm using it up so I can create the ICL. And the amount of ICL is going to be 0.1 plus 2 times 0.0729. Okay, so my equilibrium value for this is going to be 0.0271 molar. And then here we have 0.2458 molar. Let's take another sig fig back. 0.246 molar, we'll say. That's a 4. Okay, that was a good question because that actually showed us what we can use Q for practically, right? Like we were able to use that Q expression initially to figure out what is being used up and what's being formed, which we need to know before we can do this change row here. So that's a good question. All right, let's do another. So we're still using this same reaction at the same temperature. We have different values. Okay. So we have different initial pressure values here, right? But we have the same temperature, same reaction, so we have the same Kp value. In this case, we could calculate Q to prove the direction the reaction is going to go in, but we know it's going to go in the direction where it forms more product because we don't have any product. So we're going to need to create product here. And if we're creating product, that means we're using up these reactants. All right. So we can set everything up just like we've been doing. And then we'll have just 2x over here. Okay. So again, our K expression here, Kp, is going to be the pressure of the ICl squared over the pressure of I2 times the pressure of Cl2, which is the same again. So that's going to work out nicely for us in terms of being able to square root it to solve. It's always nice when we don't have to use the quadratic. All right, so we're going to plug in for this Kp expression. So 81.9 equals the ICL value squared, so 2x squared, over 0.150 minus x times 0.150 minus x. Okay, so we can rewrite that in a little more shorthand form. So I'll square the 2x squared. So it'll be 4x squared. And I'll rewrite this as 0.150 minus x squared. All right, and now we can take the square root of both sides and get rid of these exponents. Again, remember to take the square root of 81.9. Also, let me move it over. Okay, so this is going to be 4x over 0.150 minus x. Okay, so to solve this, I'm going to multiply both sides by 0.150 minus x. Okay, so we can get rid of it from this side. So we end up with 1.36 minus 9.05 x equals 4x. So let me add 9.05 x to both sides. Okay, continue over here so it's a little bit higher on the board. So 1.36 is going to equal 9, 10, 11, 12, 13. Don't judge me. 13.05x. And now we'll divide both sides. Okay. So divided by 13.05. We end up with 0.104 as our x value here. All right. Last step, we have to plug in our x value. So this will be 0.150 minus 0.104, 0.150 minus 0.104, and then 2 times 0.104. So we're going to end up with 0.046 molar, 0.046 molar, and 0.208 molar. Oh, wait, not molar, ATM. We're not at concentration right now. We're in pressure. That's what I get for not carrying my units down the whole way. Okay. Hopefully that one makes sense. Okay, we're going to look at something a little different for this next problem. And this is a specific scenario where we have reactions with extremely small equilibrium constants. Okay, so let's take a look at this information that they give us here. This is what we mean by extremely small too. You see this Kc value, how it has an exponent of -7? Like that's what we mean when we're saying extremely small. So we'll write out the reaction. Okay, and we have our Kc of 1.67 times 10 to the -7 at this temperature. Okay. And here we're told we have a 0.5 liter reaction vessel that initially contains 0.0125 moles of H2S. We're going to find the equilibrium concentrations of the hydrogen and the sulfur. All right. So the first thing we're going to need to do is find a concentration value, right? Because our equilibrium constant is based off of equilibrium concentrations. So I'm going to take I'll write it over here, 0.0125 moles of H2S divided by 0.5 liters. And that gives me a molarity of 0.0250 molar. Okay, so this is the concentration I'm going to use for my initial concentration of H2S. Okay, and I have none of this stuff initially. So now I can set up the rest of my table, or as much of my table as I can. All right, standard ice table format. I know that I'm going to be creating hydrogen gas and sulfur gas. So this will be plus 2x, and this will be plus x. I know I'm going to be using up my H2S. So this is going to be minus 2x. All right. So now I'm going to write my equilibrium rho, 0.0250 minus 2x, and x. All right. Now, when we set up the Kc expression here, well, let me set it up first and then I'll explain. So we're going to set up products over the reactants raised to the coefficients. So H2 squared times S2 over H2S squared. Okay, I can plug this in. 2x squared times x divided by 0.0250 minus 2x squared. All right. So when your K value is very, very small, okay, what this means is that if this is your reaction, for example, A plus B and then C produces C plus D. When you have a K value that's very small, that means that your forward reaction or the formation of products is not favored in that reaction. Okay, so when you have a Kc value that's tiny, like times 10 to the negative 7, that means that most of your reactant is going to stay put and only very little product is going to form. All right, what that means for us is when you're looking at the value of this term here, right? They're saying at equilibrium, our equilibrium concentration of the H2S is going to be this number minus whatever we lose, right? That's what this 2x value represents, whatever H2S we use up to make our product, okay? If our K value is very small, that tells us that whatever this value is, it's going to be really, really small because we're not making a lot of product because our K value is so small. All right. Now, if that's true, then we can assume that when we compare this 2x value to our starting amount, that 2x value is going to be so small that we can kind of just take it out of the equation. All right. This allows us to eliminate using the quadratic equation in cases where we have very small K values. Okay. And we'll check to make sure that this assumption that we're making is valid at the end of our calculation. We always have to double check, but watch how much quicker it is to solve this problem now, making this assumption that this term is very, very small and negligible, basically. Watch how much faster we can calculate x now, okay? So we can rewrite this as 2x squared times x, which will be 4x cubed over 0.0250 squared. All right, and this is going to be equal to our Kc value of 1.67 times 10 to the negative 7. So, I mean, this looks so much better to solve than a quadratic equation, right? So I am going to multiply both sides by 0.0250 squared and rewrite it. So 4x cubed Okay, I'm going to divide these values by 4. And now I'm going to take the cube root of this. Okay, so my x value is 2.97 times 10 to the negative 4. Okay, and this is a value that we assume that we can plug in our equilibrium row. Okay, before we can take that step though, we just need to check to make sure that our approximation is valid. Okay, and for that, we use what's called the 5% rule. Okay, and we're checking, we're going to compare this x value to our initial concentration and make sure that the value isn't larger than 5%, basically. If it's larger than 5%, then you have to either use the method of successive approximations to solve it, or just solve it using the quadratic, depending on what you find easier. Okay, so here we're going to take our 2.97 value. Let me write a little formula for this over here. So to find the percent, you're going to take your x value and you're going to divide it by your initial value, and then multiply it by 100. Okay, so we're going to take this x value, we're going to divide it by 0.0250, and then we're going to multiply it by 100. Okay, and we get 1.19%. That's below 5. That means that we are allowed to use this method, and we can use this value as our x value. So now we just go and we plug it back in, right? So everywhere where there's an x, we're going to plug in this value. Okay, so 2 times 2.97 times 10 to the negative 4 is going to be 5.94 times 10 to the negative 4. Okay, and our final H2S equilibrium concentration is going to be 0.0244 molar. So you see it didn't really change very much. And we don't expect it to change a lot. If the K value is very, very small, we don't expect our initial concentration to decrease by a whole lot, right? Because that small K value means that the reaction doesn't tend to form a lot of product. Okay. Let's try one more of those. Are we doing the... All right. Okay, so we're going to do the same reaction at the same temperature, but we have different initial concentrations. Okay, so here we're going to have an initial concentration of 0.1 molar H2S, 0.1 molar H2, and we'll have no S2. Okay, and we're going to find the equilibrium concentration of the sulfur gas in particular. Okay. So let's take a look at what we got to do here. Now, in this case, you can solve for Q to figure out which direction that your reaction is going to go. But because we have a 0 as one of our products, that means that when we do that Q calculation, right, it's because Q is going to be products over the reactants raised to the coefficients. Well, the sulfur is 0. So that means that our Q value is going to equal 0. 0 is less than K. That means that our reaction is going to be going in this direction. Okay. If you find it difficult to reason out the direction of the reaction, don't reason it out. Use K, and it will tell you which direction the reaction's going. But in this case, let's write this like this. We are going to be forming hydrogen gas and sulfur gas. and we're going to be using up the H2S. Okay, so for our equilibrium, it'll be 0.100 minus 2x, 0.100 plus 2x, and x. All right, let's take a look. Okay, so here we're going to have 0.100 plus 2x squared times x over 0.100 minus 2x squared. All right. And again, you know, think about this logically. If your K value is very small, that means that the amount that you're removing from your initial concentration is going to be so small when you compare it to this value that we can drop it out of the calculation. The same would logically be true then when we're looking at the hydrogen gas. This, whatever this 2x value is, it's going to be such a small number compared to the 0.1 molar H2 that's already present, because so little of the H2S is going to convert into product, that when we are adding these values together, the 2x becomes very unimportant when you compare it to the 0.1 that's already there. Okay, so we're going to drop these terms, the minus 2x and the plus 2x, we're going to drop those out of our calculation and see if we can calculate x without them, because it's a little bit easier, right? So we'll rewrite this as 0.100 squared times x divided by 0.100 squared. All right. And that's going to equal 1.67 times 10 to the negative 7. Okay. So let's see what we get for this. Okay. These are going to drop out because they're the same number. And we're going to get an x value of 1.67 times 10 to the negative 7. Let's compare that to our initial concentration now. And we'll multiply by 100. Oh, it's not this. I wrote 5%, like I'd already proven it. We're still checking right now to see if it's below. Okay, so it's less than 5%. Okay, now because our 5% rule checks out, we found our x value here. Okay, in this case, they only wanted us to figure out what the equilibrium concentration of that sulfur was. So we can plug that right in there, and we can say that the equilibrium concentration of the S2 gas is 1.67 times 10 to the negative 7 molar. Okay, and again, if that value, when you do your 5% check, when you check it and that value is above 5%, then you just go back and you can do the quadratic equation and solve for x that way. Okay. So I think we're gonna move on to some Le Chatelier questions. All right. And we'll talk through a bunch of these, and I can draw out what we need to. Okay, but a lot of these Le Chatelier questions, you have to have an understanding of, just how the reaction is shifting and what things are affecting it. So let's write out this reaction. Actually, I do want to do it on my board instead. I like to be able to draw arrows back and forth when I'm explaining this. So we have a reaction, CaO solid and CO2 gas. And we're asked two questions about it. Okay, so question one says, what's the effect of adding additional CO2 to the reaction mixture? Okay, so the way Le Chatelier's principle works is if this system that we're looking at here is at equilibrium and you disrupt that equilibrium, the reaction is going to shift in whichever direction it has to correct the disruption. Okay, so if you add additional CO2 to the reaction mixture, that means that you have too much product. Okay, so it's going to like throw off your Q value. You could think about it that way. If you have too much product, then the reaction is going to shift in the direction to kind of get rid of some of that. Okay, so it's going to shift to the left to get rid of some of this extra CO2 that we put in. Okay. The second part of that question said, what is the effect of adding additional CaCO3? Okay. If we add additional CaCO3, CaCO3 is a solid. If we add more solid, it's not going to change the direction of our equilibrium at all. What's going to affect our equilibrium is going to be the concentration of the products and the reactants that are not solids and are not pure liquids. Okay, as long as we have some of this solid present, it doesn't matter if we add or remove it. Okay, so there's no effect if we add additional solid CaCO3. It does not change our equilibrium at all. It's not going to affect the equilibrium. It's not going to cause a shift in a particular direction. Okay, let's look at the next. So you guys can look at it while I write it down on the whiteboard. Okay, so we're being asked two questions here. First question is, what is the effect of adding additional Br2 to the mixture? Okay, so again, if we're adding additional Br2, that means we have too much product. And to correct this, the reaction is going to shift to the left so we can use some of that up and kind of balance back out, get it back to that K value again. Okay. On the other hand, if I add additional B, R, and O to my reaction mixture, now I have too much reactant. So to correct this, the reaction is going to shift to the right and create more NO and Br2 product. So it can use some of this up. Okay. Another question we can ask is, what happens if we remove some of the NO gas from the reaction mixture? Okay, if we remove some of that NO gas, Well, now we don't have enough to be at equilibrium. So our reaction is going to shift to the right to try to produce more NO and reestablish that equilibrium. Okay. All right, let's look at the next one. There's a lot going on in this one. Okay. So the first question uh, asks us, what is the effect of decreasing the volume of this reaction mixture? Okay. When you're looking at changes in volume or pressure, what you're going to want to focus on is the moles of gas that are on your reactant and product side. Okay. So when you see either of these things being changed, you want to focus on the number of moles specifically of gas on your reactant versus product sides. Okay. Now, when we decrease the volume of our container, our reaction is going to shift toward the side with fewer moles of gas. Okay, we have less space, so the reaction is going to shift towards the side of the reaction that has fewer moles of gas. So we have 0 moles of gas on the left side, and we have 3 moles of gas on the right side. So our reaction is going to shift left where there are no moles of gas. Okay. Now the second part of this says, well, what if we increase the volume? Well, then we're looking at the opposite situation. Okay. When we're increasing the volume, that means that we have more space, and the reaction is going to shift towards the side that has more moles of gas present. Okay. And I just want to throw something in here about pressure, because if you think back to when we talked about gases and the gas laws, you remember there's like an inverse relationship between pressure and volume, and that kind of carries over here. So I want you to notice that when we decrease the volume, this effect that we're seeing, it's the same effect that happens if we were to increase the pressure. If we were to increase the pressure, our reaction would also shift toward the side with fewer moles of gas. Okay. So in that same thought process, if we were to increase the volume and cause this shift towards more moles of gas, that's the same result that we would get if we were to decrease the pressure. All right. So keep that in mind. The last part of that question says, what effect would adding an inert gas have at constant volume? Adding an inert gas has no effect on equilibrium. Okay. And when you're talking about an inert gas, you're talking about things like, argon, neon, your noble gases. Okay. So hopefully that makes sense. All right, let's look at this one. No, I just talked about that. Yeah, let's talk about this one. This is the last real topic, is this temperature. Okay. So when we're looking at a reaction, let's see, what do we have here? This is telling us that the following reaction is endothermic. Okay, back to this calcium carbonate reaction again. Okay, and they're saying that this reaction is endothermic. Okay, so what do we need to remember? We need to remember that when something is endothermic, that means it's got to absorb heat for the reaction to proceed. Okay, when something is exothermic, the reaction releases heat. All right, so they're telling us that this reaction is endothermic. That means that for this reaction to happen, it has to absorb heat before products can be made. That means that we can consider heat as one of our reactants. Okay, once we consider heat to be one of our reactants, then looking at the effects of changing temperature, the effect that changing temperature would have on this equilibrium, it becomes a little more clear, right? So the two questions that they're asking us here, what happens if we increase the temperature of this reaction mixture, and what happens if we decrease the temperature? Okay, so if we increase the temperature here, treat this just like any other reactant. If we increase the temperature, that means we're adding more heat. Heat is a reactant. So if we're adding more reactant, that means we have too much reactant, and our reaction is going to proceed in a forward direction to try to get rid of some of the extra reactant. Okay. So it's going to proceed to the right. Okay. Another way we can write this is we can say that it favors products. Right? Because as it's trying to get rid of that excess reactant, it ends up making more of our products. On the other hand, if we decreased the temperature, okay, we put this thing in an ice bath or something like that, well, all of a sudden, we're removing one of the reactants from our mixture. And if we remove one of the reactants, then in order to establish equilibrium, the reaction is going to try to replace it. So the reaction is going to shift in this direction toward the reactants to try to replace some of the lost reactant. So if we decrease the temperature here, the reaction is going to proceed to the left. We can say that it favors the reactants. Okay. All right. Hopefully that was a good summary for you all. If you have any questions, you can always let one of us know. And just, keep on practicing, keep on studying, and get ready for the next exam.